Hello everyone, welcome to another exciting episode of Physics with Noshir Alam. And I guess by now, by looking at the two pictures, you would have realized what the topic is. The topic for today is gravitational fields. Now, in gravitational fields, we'll talk of attractive forces and how they influence each other. So let's kick off the discussion by discussing Newton's third law. And let me remind you from Physics AS that Newton's third law has basically four conditions. So condition number one is that the forces must be acting on two different objects. In this case, there's a force pulling the Earth towards the astronaut, and there's a force on the astronaut pulling it towards the Earth. Condition number two, the forces must be equal and opposite. So if this is, let's say, F1 and this is F2, then F1 and F2 must be equal. Now you must be wondering, why are they equal although the masses are different? We'll know in just some time, but for now, believe me that this is what Newton's third law was, that the two forces must be equal and opposite regardless of the masses. And the third condition is that the forces must be of the same type, which means in this case both forces are attractive. The Earth is attracted towards the astronaut and the astronaut is attracted towards the Earth. And the fourth condition is that the forces act on each other for the same time, which means that for one instance, just think that the astronaut disappears. And if the astronaut disappears, there's no force, the whole chapter is finished. So let's bring the astronaut back. Remember that the forces must be acting on two different objects at the same time. Likewise, if the Earth decides to disappear, these two forces of attraction, F1 and F2, they will also disappear. So now it's time to discuss how we calculate the force of attraction or the force of gravity. But before that, I want to show you something very, very cool. We have this Earth and we have this spaceship, and you must understand that the spaceship can go around the Earth like this. I totally feel like a child right now with a very cool toy. Here we go. So the circle is complete. Fun part is over. Just kidding. So as you saw, my cool spaceship went around the Earth, and let's say it took a time t to finish its orbit around the Earth. And at the same time, the radius of the orbit is given by r. Now you would understand the fact that this time period is proportional to the radius of the orbit. Basically, what I mean to say is that the larger the radius, if you increase the size of the radius to, let's say, here, then obviously you'd be making a larger circle. And if you're making a larger circle, which means you're traveling more distance, it should take you more time, doesn't it? So time period is proportional to r, but later on in the lecture, we will prove this relationship, and I'm going to give you something which you might feel a little put off by, that they have a direct relationship, but it's actually t square is proportional to r cube. This I am going to prove later. Do not worry. Ye kahan se aa gaya, you will just know. But the basic idea is that the time period of my orbit, the time it takes for my spaceship to go around the Earth, is proportional to the distance from the Earth. The larger the distance, the more the time. The lesser the distance, the less the time. Or ye powers kahan se aa gayi, you will just know in some time. So hold your horses. Now what you should know is that my spaceship had a speed v. Right? My spaceship had a speed v. I'm assuming that this is a uniform circle. I'm assuming that this circle is a uniform circle. मतलब हर तरफ से distance same है. असल में ऐसे नहीं होता. Actually, the Earth is not a perfect sphere. So you cannot have the same radius r, but I'm explicitly mentioning this, that I'm assuming that this is a perfect circle, so the radius r is the same everywhere. And if you remember from my previous episodes, that we're discussing uniform circular motion, so that means my speed is also constant. And from the previous episodes, if you've seen them, I hope you've seen them, we can say that my speed v is 2 pi r, which is the distance, over time, which is the time for one circle. So 2 pi r is the distance that you travel in one circle. So one circle, the circumference is 2 pi r, and the time it takes is capital T. So 2 pi r over t, that gives you the speed of this particular spaceship. Cool. Now, you also know, as I mentioned before, that t square is proportional to r cube, which I'm going to prove later. And I'm going to use these relationships now, so you'll see what happens. So picture aside, here we go with the math. So we said that the speed is 2 pi r over t for the satellite, and we said that t square is proportional to r cube. Now, in the first equation, let's make t the subject of the equation. You would end up getting 2 pi r over v, correct? Now, let's pick up this value of t and plug it here into t square. So you will get 4 pi square r square over v square is equals to k r cube. K is the constant of proportionality, and you end up getting this result, which is 4 pi square r square over v square is equals to k r cube. Now, because your object is moving in a circle, your spaceship was moving in a circle, so we can say that there must be a centripetal force which is helping the spaceship move in a circle. So centripetal force, if you remember from the previous episode, the formula was mv square over r, where what is v? V is this thing over here. And what is m? Let me remind you, this was the Earth, and let's say this was the satellite. M is the mass of the satellite, जिसकी speed आप ले रहे हैं इस formula में. Remember that these two variables, m and v, are interconnected. So it's not possible that you're taking the mass of the Earth and you're taking the speed of the satellite. That doesn't make any sense. So it's the mass of the satellite, the speed of the satellite, and r over here is the distance of the satellite from the center of Earth. Isko small r and capital R, it doesn't matter. So Fc, the centripetal force, which is acting on our satellite here, Fc has this direction. So Fc is mv square over r. So for a second, if you look over here, you can see v square. I can make v square the subject of my equation, and I can get v square is equals to 4 pi square r square over kr cube. I hope that makes sense. I simply took v square to this side and brought kr cube to the denominator. So v square is equals to 4 pi square r square over kr cube. You can simplify this as well. R square and the cube will cancel out. So you are left with v square is equals to 4 pi square over kr. Now, let's pick up this relationship and put it instead of Fc. So Fc is equals to, by putting it instead of Fc, I meant put it in v square. So Fc is equals to m into, अब v square की जगह इसको डालें, so you'll get 4 pi square over kr bracket shut divided by another r. So when you simplify all of this, you will get Fc is equals to 4 pi square m over kr square. Amazing. 4 pi square and k, they're all constants. So what we can do is we can put all of them together, club all of these three constants together and say Fc is proportional to m over r square. Now, this m, remind yourself again, this is the mass of the smaller object. The mass of the larger object, which is the planet itself, is capital M, and the mass of smaller planet is small m. And what is r? R is the distance between them, and that's how you get Fc is proportional to m over r square. Now, coming back to Newton's third law from where we began. Now, Newton's third law suggested that this force, this one, Fc, this must have an equal and opposite reaction, right? And that reaction must be this way. Newton's third law also said that the two forces must be acting on two different objects for the same amount of time. So that means that this force Fc is not only acting on m, it's also acting on this capital M. फिर आपका ज़हन में सवाल ये आना चाहिए, तो फिर ये कैपिटल M क्यों नहीं इसके इर्द गिर्द सर्कल करता, स्मॉल m क्यों इसके इर्द गिर्द सर्कल करता है? The answer is the masses are different. The forces are the same. Mind the fact. The forces are the same, but it's the masses which are different, which is why this mass, which is the lighter mass, will always end up circling around. You can use this example anywhere. Let's talk of, let me give an example. Let's talk of the nucleus. The nucleus is positively charged, and you have an electron which is revolving around the nucleus. Now, both the electron and the nucleus, they're both getting attracted to each other. But why is it the electron spinning and why isn't the nucleus spinning? The answer is, again, the masses are different, but the forces are equal. So I hope that makes sense to you, that both of these masses, now let's get back to gravitation, but both of our masses are experiencing the same force, but the lighter mass will move, the larger mass will remain in its place. So by Newton's third law, we can say that this F, the Fc or F, whatever you want to call it, is proportional to both the masses and not just one. And again, remind yourself, Newton's third law, first condition, the forces must be acting on two different objects. So Fc is directly proportional to m into m over r square. Now, because this force Fc is also over here and over here, and you can see clearly that both the masses are attracting each other. So I can call it anything. I can call it Fg. It's a force of gravitation. It's an attractive force. Is equals to, now when you open the constant of proportionality, you get G mm over r square. Amazing, isn't it? You have ended up proving Newton's law of gravitation. जिसको ज़्यादातर लोग रटा लगा लेते हैं. You have just derived it in a very non-intuitive way. I'm not saying this is the only way of deriving it, but this is one way of deriving. This is how I derive it, so I'm sharing it with you. So again, what you should understand is that in the last chapter, we were saying that centripetal force itself is nothing. So if you have this planet and you have this little small object and it is making a circle around this planet, it must experience a centripetal force. And please recall from the previous episode that centripetal force itself is nothing. It's always caused due to something else. So in this case, if your question is, what is causing this centripetal force? You will say that it's the force of gravitation. The force of gravitation which provides the centripetal force Fc. So we write Fg is equals to Fc. And you just saw that from the formula of Fc, we were able to derive Fg. So here is Newton's law of gravitation for you again. Fg is G mm over r square. Now let's populate this on the diagram as well. Capital M is the mass of the larger planet. Small m is the mass of the smaller planet. R is the radius or the distance between the two objects. And there's a force of attraction, which is called the force of gravitation. Another very important point. These two masses, m and m, these two masses are referred to as point masses. Do not forget this. So if in the paper you get a question on how to define the law of gravitation, you will end up writing this particular formula, which is F is equals to gmm over r square. But remember that you have to explain all of these. So we will explain what G is. G is your gravitational constant, and capital M and small m are your point masses, whereas R is the distance between the masses. Now, your question should be, why point masses? Think about this. आपके planet का जो radius है, the planet, the one whose gravitational field is dominating, this radius, this is RP, the radius of the planet. What do you think is the relationship between capital R and RP? Do you think they're very close, or do you think they're very far? The answer should be that they are very, 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 very far. In value, RP is very small as compared to R. Now think about this. आप एक object को बहुत ही दूर से देखो. Like, let's say tonight you decide to go out and watch the sky. Do you see the star in its full size, or do you see a spot? The answer is you see a spot. Why? Because of the same fact that the radius of the planet and this distance, they are worlds apart, universes apart. So, because RP is extremely, extremely small as compared to the distance between the planets, these masses, capital M and small m, appear to be point masses. It's due to distance. All right? You know, I always say that if you're passionate about physics, the grade and the concepts will automatically follow. So based on the same theme of passion and, enjoying this chapter, I want you to have a very calm and close look on what the Earth looks like from the International Space Station. Enjoy. And while you're looking at it, I want you to see the beauty of nature and how lucky we are. So I hope you completely immersed yourself in that amazing footage captured by the International Space Station. By the way, did you see the green lights? They're also called the Northern Lights, or more popularly known as Aurora Borealis, if I'm not pronouncing that wrongly. And a lot of people go to watch. It's just amazing, the spectacle. Now, let's get back to our syllabus. You have this ISS, for example, and it's revolving around the Earth in an orbit. And remember that it was revolving around because it's experiencing a force which is called centrifugal force. And you know that the centrifugal force is only there due to something else. And we just had a look at it in previously, that it's the force of gravitation which provides the centripetal force. So let's start off. You know that Fg provides Fc, so I can write Fg is equals to Fc. By the way, in all the questions that you attempt, whenever you're using the word centripetal force, always mention what is causing the centripetal force in a statement. If you don't, you will end up losing a lot of marks, and the students who attend my classes already know that. Fg is equals to Fc. So let me remind that there were always two masses, capital M, which is the mass of the planet, and small m, which is the mass of the satellite. So Fg is gmm over r square, and Fc is centripetal force, and you already know the formula, which is mr omega square, mv square over r. Now, in this particular result that I'm trying to derive, I'll use mr omega square. Remind yourself, small m is the mass of the satellite. You can see it on both sides, gets cancelled. What is r? R is this distance, the radius of your orbit. So you end up getting gm is equals to r cube into omega square. And remind yourself, please, do not forget the previous episodes or the lessons that you've learned. Omega was 2 pi over t. A lot of kids just make this mistake that they say omega is 2 pi r over t because formula is बहुत similar है. Nahi, omega is not 2 pi r, v is 2 pi r over t. So don't mess up omega with v. All right, please don't screw up that relationship. Omega is 2 pi over t. So gm is equals to r cube into omega ki jagah dalo 2 pi over capital T, put a square over there, 2 pi over t, and now let's open it. So you end up getting gm is equals to r cube into 4 pi square over t square, and let's just cross multiply. So you end up getting t square into gm, and let's bring 4 pi square over here as well. 4 pi square is equals to r cube. Now g is constant, m is constant, 4 is constant, and pi square is also constant. So all of this clubbed together, you get t square proportional to r cube. Remember I told you that I'll prove this later? Here you go. Happiness. So this is the proof for a law which is called Kepler's law. Perfect. Also, I think I haven't mentioned this before, that this gravitation constant g has a value 6.67 into 10 raised to power minus 11. All right, just to give you a quick example on how to use the previous relationship. The previous relationship was t square proportional to r cube. So please take note that this question can come in many different ways. For example, they could say that you have this central planet P, and then there's a small satellite S1 around it, and then there's another satellite S2 in another orbit around the same planet P. Now, S1 is at a distance R1 from P, and S2 is at a distance of R2 from the same planet P. And what they'll do is they'll give you the time for S1. For example, they'll give you the time as T1, and they'll ask you to calculate time T2. In that case, what will you do? All you would do is, since planet P is the same for both the orbits, you could apply Kepler's law. And Kepler's law is that T1 square over T2 square is equals to R1 cube over R2 cube. Now, you'll have the value of T1, you will have the value of T2, and you will also have the value of R1. So you can find the value for R2. और अगर इस question के हिसाब से देखो तो you're given T1, you're given R1, you're given R2. You can easily find what T2 is just by basic manipulation. So that's one category of questions. Another category of questions could be, let's say this one. So this is a part of some question. I've just extracted the relevant part for you. So it says the radius of the orbit of planet R is R and the orbital period is T. So there is some central planet, basically, and that planet is, again, P. Or around that planet, you have these different C, E, G planets. So C is 9.6 into 10 power 10, uska ye time square value given hai. E is another planet around planet P. This is the radius and this is the time square value. Well, let's move forward. First of all, they say that the radius cube is proportional to T square. You should understand that this part that they're saying, this is Kepler's law. So you should be able to identify that it's a question on Kepler's law. And then they're saying that show that this is the constant. So I've shown this proof earlier. You put Fg provides Fc, and then you write Fg is equals to Fc, and then you say gmm over r square is equal to mr omega square. Then up is r square ko idhar le aao, r cube. If you've forgotten it, move this back, I think, a couple of a minute, and you'll know what exactly are we talking of. And over there where I put a circle around the constant, that constant will be gm over 4 pi square. Well, that's one category of questions. Now, given this, what they ask you to do is कि इसको सामने रखते हुए prove something else, do something else. And here is the question. So they say that use data from this figure 1.1 for the 3 planets to calculate the mass of the star. Now, all of these planets have been orbiting another star, and you have to calculate the mass of the star now. So I just did the calculation for you. I simply used r cube is equals to kd square, and or k की value was gm over 4 pi square. M is the mass of the big planet, जिसके इर्द गिर्द ये छोटे planets या छोटी satellites revolve कर रही हैं. R is the radius. I picked up the 9.6 10 power 10 value. As you can see, I put a cube around it, is equals to G value 6.67 10 to minus 11 into M nikalna. Be careful over here. They've already given you the time square value, so just use the time square value. And 4 pi square per divide karo, this is the answer. Now, if it's popping in your mind that why did I just specifically use planet C's value, I could have used planet E's value. Yeah, you could use that. You'd get the same result. Similarly, you could use planet G's value, plug it over here, and you'd get the same result. So doesn't matter which value you use, all 3 values will give you the same result. Alright, so the next topic that we're going to discuss is gravitational field strength. And gravitational field strength is defined as the force of gravitation acting per unit mass. Now, force of gravitation का जो formula आपने किया था पहले, that was gmm over r square. You divide this by the smaller mass, the mass of the object which is rotating or which is spinning. M and M will get cancelled. So gravitational field strength turns out to be equal to gm over r square. Capital R likhein or small r likhein, doesn't matter. So gm over r square. Now, this tells you of an inverse square relationship between gravitational field strength and the distance from the center of the planet. Let me explain. So if this is planet P again, and this is planet P, and you are moving from point A to point B. So at point A, your strength of gravitational field is Ga, and at B, the strength is Gb. Let's say this distance is R1, and this distance is 2 times of R1. So the first distance r1 and second distance are 2 times of r1, then GB will be equal to GA divided by 4. That's what we mean by an inverse square relationship. कि अगर distance double हो रहा है तो gravitational field strength 4 times reduce होगी. Remember that in the inverse square relationship, we call it the inverse square relationship because the two are inversely related, which means that gravitational field strength is inversely proportional to r square, which means that if your distance doubles, then your gravitational field strength decreases by, not by half, by 4. So gravitational field strength of B is equals to gravitational field strength of A divided by 4. That's one use. Another way to interpret this is that if I give you a graph and I say plot the gravitational field strength Newton per kg, from the formula you can see that the force Fg is measured in newtons and the mass is measured in kilograms. So the gravitational field strength is given Newton per kg, and over here on the x-axis you've got distance in meters, and these distances are going to be very, very large. So let's mark this distance. This distance is the surface of the planet. All right, so when you're on the surface of the planet, the gravitational field strength has its maximum value. When you're on the surface of the planet, the gravitational field strength has its maximum value, and then as the distance increases, you know that this is an inverse square relationship. So you know as the distance increases, the gravitational field strength keeps falling exponentially. You must understand this, that as the distance increases, the gravitational field strength follows this curve. It falls exponentially. Acha. Now, we don't have the time to prove in a lot of detail, but within the surface of the planet, the gravitational field strength is a constant straight line all the way to the surface of the planet. So this blue region over here, this represents within the surface of the planet, and this region, the one after the blue region, let me show it, this region over here shows beyond the surface of the planet. So if you're beyond the surface of the planet, you follow the inverse square relationship, and if you are within the surface of the planet, you follow a direct relationship. This can be proven, but right now, due to shortage of time, I cannot prove it. But you should be fairly comfortable using this equation, which is gm over r squared is equals to g. A very, very important thing to note is that for Earth, the gravitational field strength has a maximum value of 9.81 meter per second square. And that value occurs when you are on the radius of Earth. So 9.81 meter per second square की जो value होती है, this only occurs when you are sitting on the surface, over here, or over here, or over here. Anywhere on the surface, and this value will be maximum. So let's say mass of Earth is me. So I can write this as G is equals to GME over, now this is the radius of Earth, over RE square. So remember that if they have said that this value of G is 9.81, only then can you do this substitution, that GRE square is equals to G times mass of Earth. ये बहुत सारी जगहों पे प्रूव में भी आएगा, and you will be stuck and be questioning कि कहाँ से इसने GRE square को GME लिख दिया है या GM लिख दिया है. Remember that the value of G that they were assuming is 9.81. At that time, the distance that you are sitting at is the radius of Earth, so RE square goes there, and this is equals to GME. G is gravitational constant, and ME is mass of the Earth. All right, so let's finish this topic off with a question. Again, a part of the question from the past papers. It says over here that on figure 1.1, sketch a graph to show the variation of free fall with distance x from the center of the planet. Try to understand, center of the planet से distance measure किया जा रहा है और कहीं पे भी जाएंगे तो that distance is x. So when we were discussing this concept of gravitational field strength, we said that when you are at the radius or the surface of the planet, that is when your gravitational field strength is maximum. So I want you to look here that when you are at r, that is when your gravitational field strength will be maximum. 1g means full value of gravitational field strength. Don't make the mistake of starting from 0, because 0 means that you are over here, and over here you don't have a gravitational field. Your gravitational field increases uniformly until you get to this part, and at this part you are at the surface. Surface का मतलब होता है radius of the planet बैठे हुए. So you will be over here, and you mark your first point over here. Then I told you that gravitational field strength is inversely proportional to r square, inverse square law. So if the distance doubles, that means that your gravitational field strength decreases by 1/4. So 1 को 1/4 पर divide करो, and I'm guessing you get 0.25. So your next value would be here. And then when you quadruple the distance, which means you increase the distance by 4, then gravitational field strength divides by 16. So 1/16 is 0.0625 of the original value. So original value was 1g. You divide that by 16. Why do you divide that by 16? Because g is inversely proportional to r squared. So if r is going up by 4 times, the gravitational field strength will go down by 16 times. So 0.0625 को अब आपने ढूंढना है. I'll help you how to find it. Here we go. We zoom in and have a close look. So somewhere on 4r, you are trying to find this value, right? But you can't find it. So यहाँ पे notice करो that you have 10 boxes, and 10 boxes, the value is 0.25g. So you divide 0.25 by 10. Do this in your calculator. You will get that the value of one box is 0.025g, the value of one box. Now you want 0.0625. This is what you want to find, and the value of one box is 0.025. You divide them, you get 2.5, which means at 4r, when you reach 4r, you go one box up, you go 2 boxes up, and this is where the value should be. So you go and mark this point over here, and this is 0.0625. And then what do? Let me zoom out so we can make the graph now. You've marked the 3 values. All you need to do now is join them with a smooth curve. Let me try, and here we go. So like this, and here we go. So that's the curve that you should get. And with this, we'll wrap up this lecture for today. I'll see you in the next episode, and we'll hopefully try to finish off this topic. Cheers, guys. Have a great day.